Guys, yesterday we took a look at standing waves mathematically for the first time. A couple of days ago we did a demonstration where we showed you standing waves. You guys know what they are, right? Waves are being produced at one end. They're going down a string, or they're going down air, or they're going down some medium. They reflect off of a boundary. They come back and they interfere to produce an interference pattern. Now, normally that interference appears to be random. It isn't random. It just looks to be random. But at very specific frequencies, certain frequencies that we call the resonant frequencies, the natural frequencies of the string or the air or whatever, we see a very special pattern, a pattern that makes it appear as if the wave is not moving, standing still. We call it a standing wave. The first one that would occur when we have a string that's attached at both ends, like we did in the demonstration we did a couple of days ago, would look like this. The second one that we would see would look like this. The third one that we would see would look like this, and so on. Notice in the first one, we have one antinode, that's the bump in the middle, the antinode, and two nodes. So one antinode, two nodes. In the second one, we see two antinodes and three nodes. And then we see three antinodes and four nodes, and the pattern would keep repeating itself. Now, yesterday we derived an equation that described mathematically each of these standing waves or each of these resonant frequencies that occur. We defined the length of the string as L, and then we said L was equal to, in this case, a half of a wave, a half of lambda. We rearranged that and said lambda is equal to 2 times L. Here we said L was equal to lambda, the entire wave, right? From equilibrium through the equilibrium and back to the equilibrium again, an entire wave. So we'd say L is equal to lambda, or lambda is equal to L. In this case, we would say L is equal to 1.5 waves, or we would say 3/2 lambda, or lambda is equal to 2/3 L, and so on and so on. We don't need to go anywhere past that because you guys know where we're going with this, right? There ends up being a pattern that allows us to not even worry about the second, third, fourth, and so on, because we can just deal with the first one and then multiply it by a certain number to get the other ones. All right, F is equal to V over lambda, as it is in all of these cases. F is equal to V over lambda. And then we sub in for lambda, in this case 2L. So it would be F is equal to V over 2L. Call that the first harmonic. That's the first resonant frequency of the string that's vibrating back and forth here. Okay, whatever that frequency is, calculate it, right? V divided by 2 times the length of the string. Whatever you get for the frequency is the frequency at which you should expect to see the pattern that we show you in the diagram there. The first standing wave, the first harmonic. Now, the second one, the second standing wave, or the second resonant frequency, this one right here, would appear at V over L. It's V over lambda, but lambda is L, so it would just be V over L. Now, we could say that was 2V over 2L, same thing, right? 2V over 2L is the same as 1V over 1L. It's twice the value of the first harmonic, so we're going to call that the second harmonic. And it might not be a bad idea even just to write it like this. F2 is equal to 2 times F1, if this is F1. Well, the third one down here, F is equal to V over lambda again. F is equal to V over 2/3 L. We can simplify that a little bit and say 3V over 2L, which you can see there mathematically is 3 times the value of the first one. Therefore, we're going to call it the third harmonic. And we can make this look a little bit simpler simply by saying F3 is equal to 3 times F1. And F4 would be 4 times F1, and F5 would be 5 times F1, and F17 would be 17 times F1, and so on, and so on, and so on. Does that make sense? This only applies when you have both ends of the string attached. Okay, if one end of the string is free to move, like the demonstration we did in the library the one day with the slinky, where it was not attached at the other end, you could see, if I produced the wave pulse at the right frequency, you could see a standing wave produced there. But it wouldn't be these ones. And the frequency at which it would happen wouldn't be this frequency, because it would be one end that wasn't attached. We'd see a different thing. And we'll go through that in just a few minutes, how we would analyze that situation. All right, we had some questions for homework on that worksheet, that microscopic worksheet. Questions 1 to 8 on page 1 and 2. Any issues with any of those 8 questions on the first part of that worksheet? All right, our homework yesterday was the worksheet. We're going to go over questions 6 and 7. I think we went over number 8 yesterday, didn't we? Take a look at number 6 here. It says a string on a musical instrument vibrates in 3 segments at a frequency of 335 hertz. If it vibrates in 3 segments, like this, that's like the third harmonic. That's F3. If the third harmonic is 335 hertz, then what will the fourth harmonic be? Because that's what we're looking for, really, right, is the frequency of the fourth harmonic. What we want to do in this case, okay, is calculate the first harmonic. If the third harmonic is 335, then the first harmonic would be 1/3 of that, right? If we go back to those pictures that I drew here and the equations that I derived, you see that the third harmonic is 3 times the first. Usually we have the first and we want to find the third. This time we have the third and we got to find the first. So let's divide that by 3. When we do that, we should get 111 So there's the frequency of the third harmonic. The frequency of the fourth harmonic, sorry, that's the frequency of the first harmonic. The frequency of the fourth harmonic is 4 times the frequency of the first, so it's going to be 4 times 111.6667, which is going to give me about 446, I'm thinking. Oh, 447. 447 hertz. Is that okay? Hugh, is that okay? So we didn't end up needing to use the equations we derived at all, other than recognizing that the first harmonic is 3 times the first, and the fourth harmonic is 4 times the first. Next one was number 7. It says the fundamental frequency of a 27 centimeter long string is 637. What's the fundamental frequency of the same string if it was 22 centimeters long? Here's what you got to remember for this one. The guitar string doesn't have a different speed of a wave in it depending upon where you put your finger on the fret. Put your finger on a fret, it changes the pitch, but only because it's changing the length of the string. The speed of the wave in the string is the same unless you tune the guitar. If you turn the little tuner, okay, then it's going to tighten or loosen the string, going to change the speed. Putting your finger on a fret doesn't do that. The speed stays the same. The frequency will change, but the speed stays the same. Now, that begs the question. We talked earlier in this unit, said once a sound has been made or once a wave has been made, frequency doesn't change, right? Speed can change, but frequency doesn't change. Now we're saying speed stays the same, but frequency changes? Yeah, we are saying that, but it's a different scenario. Okay, we were saying frequency remains the same once a wave has been made. Hey, listen, the soldiers went from the parking lot to the swamp in that analogy that we had. The speed changed. The frequency didn't change because it was the same wave. Here, we've got a certain wave being produced. Then we change the length of the of the string by putting our finger on a fret, and we make a new sound. Of course, you can have a new sound, a different pitch when you make a new sound, right? The length of the string changes, therefore the frequency will change. Okay? It's not like we got one frequency, one sound going from one to the other. It's a new sound. What stays the same? The speed stays the same. Didn't stay the same when we went from the swamp to the parking lot. Well, that was going from one medium to the other. Here we're going from string to string. Speed's not going to change. So what I want you to do here is to find the speed. We're dealing with a fundamental frequency, so F is going to be equal to V over 2L. Let's find speed by saying 2L times F. 2 times 0.27 times the frequency of 637. Who has a value for that? Thank you. Gives me 344 meters per second. Now, if the speed stays the same when we change the length of it, let's rearrange the same equation to solve for L. It becomes V over 2 times F. Use the same speed, 344, divided by 2 times, no, sorry, we're solving for F here now, right? Again, F is equal to V over 2L. 344 divided by 2 times 0.22. And when we do that, we should get 782 hertz. We get a number that's bigger than it was the first time. Would you expect that? Okay, listen, I'm not a guitar player, but I know intuitively that when I put a finger on a fret and pluck the string, I'm going to get a higher pitch. I get a higher note, right? That's exactly what we got here. We started with 637, we made it shorter, and we got a higher number for frequency, which is exactly what we should get. And finally, question number 8 says the fundamental frequency of a string that's 25 centimeters long is 441. We want to produce a fundamental frequency, same string, new frequency. How long must the string be now? So kind of the same question as number 7, right? Except that in number 7, we were looking for the new frequency, and this one we're looking for the new length. Once again, we're going to say V is equal to 2LF. Okay, it's this equation rearranged. It's 2 times 0.25 times 441. We get 220.5 meters per second. Now the speed stays the same, but this time we're looking for length. It's going to be V over 2 times F. So 220.5 divided by 2 times 440. 2 times 525. What would you expect to get here? Would you expect to get a longer string or shortened string? Pitch is higher. Longer or shorter string? Shorter string, right? When we do the math, we do get a shorter string. It works out to be 0.21 meters or 21 centimeters. 4 centimeters shorter than it was. Makes sense, right? The frequency goes up by 20%. The length of the string goes down by about 20%. Good? Let's take a look at a new situation now, still involving standing waves, but this time not involving a string that's fixed at both ends. This time let's look at maybe a water bottle, or maybe it's an instrument, maybe it's a flute that's closed at one end and open at the other end like the water bottle is, or maybe it's a clarinet that's fixed at one end or closed at one end with the reed and open at the other end, okay? Just like the water bottle is. When I blow across the top of this water bottle, there's dozens of different frequencies that are set up in this water bottle. Dozens of different pitches of sounds. But most of those pitches or most of those frequencies die out right away. How come? Why do they disappear very, very quickly? Most of them, not all of them, but most of them. They don't correspond to the resonant frequency of the water bottle. The water bottle has a resonant frequency or more than one resonant frequency corresponding to the standing waves that would be produced. Okay, when I blow across the top of the water bottle, dozens of frequencies are produced, but most of them that aren't standing waves or aren't resonant frequencies disappear. They die out. So what you hear right now when I blow across the top of this bottle is likely the first harmonic that's produced. In other words, the first standing wave that's produced or the first resonant frequency of that water bottle. If I turn the water bottle over on its side, then it's going to look something like this. You got a fixed end right here, and then you got an open end, a closed end and an open end. For the water bottle, the open end would be obviously the top of the bottle. The closed end would be where the water is. You guys know that I can change the length of this easily, right? Drink a little bit. What are you going to hear, a higher pitch or lower pitch? A little bit of a lower pitch, right? Why? Because I lengthened the air column. I made the water bottle longer by taking water out of the water bottle. The first one that you would hear would correspond to this. Now that's different than it was for the string. For the string, I had an antinode in the middle, and I had a node at both ends. So antinode in the middle, a node at both ends. When you have a fixed end or a closed end for an instrument or anything else like a water bottle, you'll still have a node. But when you have an open end like you do in the water bottle or like you do at the end of a flute or like you do at the end of a clarinet, you're not going to have a node, you're going to have an antinode. So the first harmonic that's produced, the first standing wave or the first resonant frequency looks different than it does for the strings. The second one also looks different. You have to have that node at the closed end, but you have to have the antinode at the open end. So it's going to look something like this. We went from one antinode and one node to two antinodes and 2 nodes. And then, of course, we're going to go to 3 antinodes and 3 nodes. The length of the air column, or the length of the water bottle right down to the level of the water, we're going to define once again as L, just as we did with the strings. The length of this is not, however, going to be half a wave. Here's my wave. If I'm going from here to here, and that's all I'm doing there, right? How much of a wave is that? It's a quarter of a wave. Good. So we're going to say L in this case is not 1/2 of a wavelength, but rather 1/4 of a wavelength. Therefore, lambda would be equal to 4 times L. What about the next one? So we're going from here down to here. How much of a wave is that? Yeah. No, this would be a half, right? How much is that? That's going to be 3/4 of a wave, right? Half of a wave. This would be a full wave. We're going 3/4 of a wave there. So I'm going to say L is equal to 3/4 lambda. If it rearranges that to solve for lambda, I get 4/3 L. And the last one here, I'm going down here, back up here, all the way to here. That's going to be 1 1/4 or 5/4 as an improper fraction. We don't have to make it an improper fraction, but it makes the pattern easier to see. All right, let's derive the equations now. For the first one, we're going to say F is equal to V over lambda. F is equal to V over, well, lambda is 4L, so it's going to be V over 4L. Remember what it was for the string that was attached at both ends? The first harmonic was V over 2L. Now it's V over 4L for this one. The water bottle, the clarinet, the flute that's fixed at one end, closed at one end, open at the other. We're still going to call this the first harmonic, though. It just occurs at a different frequency than it does for guitar, for a couple of reasons. One, because the equation is different. Two, because the speed of sound inside that water bottle is different than the speed of sound in the guitar string. So you got a guitar string the same length as the water bottle, you're not going to hear the same pitch, because it's going to have a different resonant frequency. Next. Again, we say F is equal to V over lambda, but this time lambda is 4/3 L. F is equal to V over 4/3 L. Or if we simplify it, we say F is equal to 3 over 4 times V over L. How does that compare to the first one? Remember we had V over 2L, then we had V over L, or basically 2V over 2L. V over 2L, 2V over 2L. It was twice the first harmonic. What is this one? V over 4L, 3V over 4L is not twice, but triple. It's triple. There is no second harmonic. There is only a first harmonic and a third harmonic. There is no standing wave that's set up in an air column that's fixed at one end and open at the other end that is twice the first harmonic. Only 3 times the first harmonic. Let's try the next one and see if we start seeing a pattern. V over lambda, F is equal to V over 4/5 L, or F is equal to, divide by the fraction there, multiplied by the reciprocal, 4/5 V over L. This one is 5 times the first one. We're going to call that the fifth harmonic. I should also write in as a reminder that this is 3 times the value of F1, and this one is 5 times the value of F1. So here's the deal. When you got a guitar that's attached at both ends, you can have any harmonic, first, second, third, fourth, 37th harmonic. When you have an instrument that's open at one end and closed at the other end, it could be something like the slinky not attached as I was dropping it from the atrium there, right? But more likely it would be something like a water bottle or a musical instrument. You don't have even harmonics. You only have odd harmonics, first, third, fifth, seventh, ninth, and so on. The good news is, if you remember that, it's still just as easy to solve as the problems that you did yesterday were, because Third harmonic is 3 times the first, and the fifth harmonic is 5 times the first. What about if you got some kind of instrument that's open at both ends? I don't even know an example of that, to be honest. Maybe just a pipe. You got a pipe that's open at both ends and you blow across the end of it? I don't know. You're going to get standing waves set up there, but this time it's not going to be antinode and node. It's not going to be node and node. Rather, because you have 2 open ends, it's going to be antinode and antinode. So you start off in the first harmonic with 2 antinodes and 1 node. Then you're going to have 3 antinodes and 2 nodes. And then you're going to have 4 antinodes and 3 nodes. Let's draw our wave out again. How much of a wave do you see in the first one? Well, we're going from here down to here. How much of a wave is that? Half, quarter, third? No. No. You'd have to go back up to here to be your complete wave, right? Yep. That's half a wave. So again, just like we did with the guitar that was attached at both ends, we're going to say L is equal to a half of lambda. Lambda is equal to 2L. Here we'd say L is equal to lambda, or lambda is equal to L. Here we'd say it's 1 1/4, or L would be equal to, 1 1/2, I should say, or L would be equal to 3/2 lambda. Lambda would be 2/3 L. Start deriving our equations, and you're going to start seeing something that you recognize, I hope at least. V over lambda, or F is equal to V over 2L. V over lambda, or F is equal to V over L. V over lambda, or F is equal to V over 2/3 L, which is the same thing as saying F is equal to 3 over 2 V over L. Remember these equations? Recognize them? Same as they were for the guitar, right? When we had 2 fixed ends. Here's the deal. When you have 2 ends that are the same, whether it's a guitar string that's attached at both ends, or whether it's something like a pipe that's open at both ends, the equations that describe the resonant frequencies are exactly the same. We get the first harmonic right here. We get the second harmonic right here, which is twice the value of the first harmonic. And we get the third harmonic right here, that's 3 times the value of the first harmonic. If, on the other hand, you have 1 open end and 1 closed, 2 ends that are different, then you don't have even harmonics. You only have the first, the third, the fifth, the seventh harmonic, the odd harmonics. Now, I'm not suggesting to you that if you blow into a pipe that's 30 centimeters long, you're going to get the exact same sound as if you pluck a guitar string that's 30 centimeters long. The equation that describes the frequency will be the same, but the sound won't be the same. Why not? What's different about the guitar versus the water bottle or the pipe? I should say pipe here, yeah. Not a water bottle. Yep. The speed, yeah. The speed of sound in the guitar string is much, much greater than the speed of wave would be in air. So, even though the equation that describes it is the same, and there is a first, second, third, fourth, fifth harmonic, any harmonic, the actual frequency that you would hear at a given length would be different because of the speed difference. All right, good news. Solving problems involving these, which we call, by the way, open air columns, because they're open at both ends. Problems involving open air columns, exactly the same as we had for strings. Exactly the same as the stuff you did yesterday. The ones for closed air columns, be careful with that name, closed air columns, open at one end, closed at the other. Closed doesn't mean it's closed at both ends. Just closed at one end. A closed air column, equations are different. It's going to be a little bit different than the problems you did yesterday because the equations are different and because there are no even harmonics. But if you remember those two things, difference in equations and the fact that there's no even harmonics, then they become just as easy as the questions you did yesterday. What I'd like you to do now, guys, is take a look at Take a look at the example that we have here, which will lead us nicely into the last 2 pages of the worksheet that I gave you yesterday. The example says, what are the frequencies of the first 2 harmonics observed in a 40 centimeter long air column if the temperature is 30 degrees Celsius? In air, the speed of sound is 331 meters per second plus 0.6 times the temperature in degrees Celsius. So that'll give us the speed of sound. 331 plus 0.6 times 30 gives me 349 meters per second. That's the only reason we're given the temperature, is to find the speed of sound. That only works in air. Okay, if you got a guitar string, you can't do this. Okay, this equation works if you're dealing with air at standard pressure. Now that we have the sound, though, we know the first harmonic for an air column, a closed air column. I should have said closed air column, by the way. The first harmonic for a closed air column is V over 4L. For an open air column, it's V over L. Okay, closed air column, V over 4L. Let's find the first frequency, the first harmonic. It's going to be 349 meters per second divided by 4 times the length of it, which is 0.40 meters. Do that math, we end up getting 218.125, which we're going to round to 218 hertz. There's my first harmonic. Now we're looking for not just the first harmonic, but we're looking for the next one as well. What's the next one? We could derive an equation, or we could just multiply the first one by, what is it, Mitch? 3, good. Because there is no even harmonic. Okay, if this was an open air column or a guitar, we'd multiply this by 2 to get the next one. But because it's a closed air column and there are no even harmonics, then we're going to multiply it by 3. So we'll say F3 is equal to 3 times F1. Let's say it's 3 times 218.125, which when we do that, we should get 654, I think, 0.375, which is 654 hertz, the 3 digits. So first harmonic, 218 hertz. Unlike the strings that we did yesterday, the next harmonic is the third, which is 3 times the value of the first. Let's take a look at the questions that you have on your worksheet now. It's page 3 and 4 of your worksheet. I'd like you to do all of those questions, please.